Good morning, everybody. Today, I want to pick up where we left off last week. I know we did not get to work all of the trig integral problems we wanted to. And so I am going to extend our homework from last week a little bit to make up for the fact that I was out last Friday. Sorry about that. Made the mistake of going to the gym and pretty much immediately got sick. So, coming back to reality. Get this up. And we're over here. All right. Last week's homework, which was, I think, come on, focus. One. Come on. Homework 4, right? Yeah, homework 4 for you guys too. Okay. So homework 4 will be extended through to this Friday. And that should give you plenty of time to finish up anything that you haven't gotten done yet. If you submit an extension request already for it, don't worry, I'll go through and grant those. But for everybody else, I will be extending that homework just because I know we didn't get the time to work all the examples we could have because I was out last Friday. We are going to start talking about new stuff this week. Before we do that, though, I want to work just one or two problems from that homework setter from section 7.2 on trig integrals to kind of get us back up to speed, because the next section, section 7.3, so this week, we talk about my favorite mechanism for integration. I'm going to cover trig sub. And I also want to talk a little bit about partial fractions. Now, the partial fraction conversation tends to be a little bit long, so we might start on partial fractions this week and then finish it next week. We'll see. Trig sub is section 7.3. Also, given time, we'll talk about partial fractions. Which is section 7.4. Now, in truth, partial fractions shouldn't be new to you. Pre-calculus class, a decent pre-calculus class, should teach you how to do partial fraction decomposition, PFD. But I know that the reality of the situation varies quite a bit depending on with whom you took the MAC2312 class. And in 1147, sometimes it gets squished out altogether. But the main focus this week is going to be trig sub, section 7.3. And there will be a new homework that I'm going to open up today, and it will be due next Monday probably. Also, we're getting close to exam 1. So I want to take a look at the syllabus with you guys and make a quick announcement about that. So of course, anytime you're curious about what's going on in the class, when things are going to happen, or what sort of things you should be doing, the syllabus is your friend. There's nothing like that coming up, right? Yeah, no. All right. So we are right about here. We're a little bit behind. That's okay. This week we're going to talk about trig sub and partial fractions, which normally would be a week 4 thing, even though we're in week 5. That's all right, because we missed the Friday and then we missed Memorial Day the week before. Section 7.5 doesn't have anything new in it. You see, section 7.5 is just a summary of integration techniques. So it's just a review of all the stuff that we did in 7.1 through 7.4. So this week, trig sub, partial fractions. Next week then will be section 7.5 and exam 1. So you can, I will go ahead and set the date now. A week from this Friday, that's the 19th of June, we will have our first exam. So let me switch back over here. And it will cover sections 5.5, which was on regular substitutions. 6.1, which is on areas between curves. 6.2 and 6.3, which are on volumes. 6.4 or 6.5? That was average value. I think we skip over 6.4, right? Yeah, 6.5. And then 7.1, which is on integration by parts. 7.2, which we are finishing up today on trig integrals. 7.3, which is on trig sub. 7.4, which is partial fractions. And well, that's really it. 7.5 is like a summary of techniques. Okay. Now, I may end up moving the exam. A week from this Friday is June 19th. But I think that this timeline will work well for us. I'm not too stressed about this. This looks good. However, if we happen to, for whatever reason, take a long time to get through the section on partial fractions, I might bump that to like the Wednesday of the following week or something like that. We'll see. But if you're the sort of person like me who really likes to plan ahead, I would plan to have the exam on June 19th, a week from this Friday, which means this Friday I will be giving you the study guide. Remember, the study guide is a collection of problems that you guys are intended to work the week leading up to the exam. And I expect you to come talk to me about at least one or two of those problems in office hours or via email. I don't really care how you do it, but you got to show me your work on the study guide before the test. This is for your own good. It's not to do with the grade. The grade on the study guide isn't going to be affected by that conversation at all. It's for your own sake, because when I grade your exams, I'm going to be grading your work. You really want me to take a look at your work before the exam so I can say, oh shit, you're leaving this off here every time and I'm gonna have to take a half point off if you do that every time on the test. Little things like that, right? So if there are things that need help in your work, if there are things that need to be improved or organized or something like that, that's the purpose of the study guide, is for you and I to have something about which we can have a conversation that is focused on the exam material and will help you with the exam. The exam will probably take place in WebAssign, but the majority of the credit will not be coming from WebAssign. So the way it'll work is this way I am able to use proctoring software like HonorLock. So let's write this down. You should put this in your notes. Exam. Be in WebAssign. Proctored by HonorLock during class time. All right, so instead of our class meeting on that day, you will open Canvas, you'll go to the HonorLock tab, and you'll click like Launch Proctoring next to, it'll say Exam 1. It doesn't say that yet, but it'll be there. The important thing for you to remember is that you must write out solutions to every problem. And then scan, upload your written work as soon as possible after finishing. So I'm going to create a slot in Canvas where you can upload the scans of your written work. So every problem on the test, you will write out a full solution to on your own paper. Please, one problem per page, one problem per side of the page. It needs to be neat. That's what I'm going to grade. The WebAssign stuff will be worth some amount of the grade, but the majority of the credit on the test is going to come from me grading your actual work. There's two big reasons to do this. The first one is partial credit. Nobody wants to get a 0 on a problem because they switched a 9 with a 6 or something like that, and that's what would happen in WebAssign if we just went with the WebAssign grade. That sucks. So partial credit, that's real big plus for you guys. You definitely want that in Calc 2, I promise. The other thing is this allows me to verify that your work is actually your own. Not that I think any of you would specifically go out of your way to cheat, but I know that in an online class, that temptation is very real. If I don't have written work for a particular problem, it's not just that I won't be assigning partial credit, I will be removing credit. So for every single problem on that test, you need to write out your full solution, scan it. I recommend Cam Scanner. It's a great scanning app for iPhone and Android. It's what I use. It produces really good looking PDFs. But there's two purposes for that, right? One, partial credit, which is like a good thing for you. And then the other is so that I can see that your work is actually your own and you're not just giving me something from somebody else or Symbolab or whatever. Super duper important that you write out the solutions as you work the test and then scan and upload those immediately after you finish the test. I'll give something like a 2-hour window overall for the test, and I'll be posting very detailed instructions to Canvas. So right now, just think of this as, I'm just explaining. But it'll be during class time, so it'll be from like 11:30 to 1:30 or something. You can take the test. And then as soon as you finish in WebAssign, you need to scan and upload your written work for each problem. That is how I will be grading your test, and that's where the majority of the credit will come from. The majority of the credit is not going to come from your WebAssign score. It's going to come from your written work, which I will grade. So I need those scans. If I don't have written work for a problem, it's not just going to be that it doesn't help you, it will hurt you, right? It'll be like getting a 0 on the free response portion of that question, which is worth more than the actual answer in WebAssign. Any scanning app is good. I've seen lots of them. I've probably over the last, 4 or 5 months since this COVID-19 stuff happened, 3-4 months, seen outputs from 4 or 5 different scanning apps. I don't know Genius Scan off the top of my head. It was asked in chat if Genius Scan is acceptable. Find one that you like. Play around with 1 or 2 and find one that generates good-looking PDFs. They will need to be PDFs. I won't be able to accept HIC or JPEG or PNG files. They have to be in PDF format because that allows me to annotate. So I'll be able to go in and write comments. If you have an iPhone rather than an Android, I have been told that the Notes app can do a decent job scanning and that it will output as PDF. That's fine with me as long as it's legible. You're welcome to use whatever app you want, as long as you get me a good, readable, legible PDF of your work within a few minutes of you finishing the test in WebAssign. Okay, so that's the rough outline here for how this is going to go. Are there any questions for me regarding the exam? What's expected, how it's going to work, stuff like that? So if your phone, try downloading one of those scanner apps and see if you're able to get something decent out of it. If not, let me know and I can work to try and get you something that will do the job. Dalton asked, are the homework questions harder or easier than the test questions? It varies. There are homework questions which are harder than your average test question. There are homework questions which are easier than your average test question. Think of it this way. There's going to be somewhere around 10 questions on the test, and each question is going to be targeted at a specific skill. So there will be a question that is targeted at your ability to do looping integrals by parts. There will be a question that's targeted at your ability to do U-sub, where you have to change bounds and maybe swap some things around with the differential. There will be a question for each of those things, but I won't be mashing a bunch of them together. So there won't be a problem where you have to do like trig sub, looping IBP, and then U-sub. I won't tangle all that stuff together. They'll be fairly focused, but they'll be medium difficulty questions. They're not going to be super easy. They're not going to be super hard either. If you like, that's again what the study guide is good for. The study guide will have exam level problems on it. So I'll be publishing the study guide this Friday. It's going to be a WebAssign thing, and you're going to do the same sort of thing there. You're going to write out solutions and scan them to me, and that way we can talk about them. We can talk about your notation. We can talk about anything that we need to. And that should also give you a feel for the level of difficulty, the questions that I'll be putting on the test. Those are good questions. Any other questions about this stuff? Okay, I'm going to fill up my coffee, and then we can look at an example problem or two from section 7.2, and we'll move on to 7.3. Yes. Yeah, so one of the requirements for this class is a webcam, laptop, or a computer capable of running honor lock. It's not the best thing in the world, but it is getting better. You no longer have to fuck around with tokens. The whole token system is gone. So it's not going to require any of that, but you will need a webcam that's capable of recording like an ID in sufficiently high fidelity to verify that it is you. You will need to be able to move the camera around to scan the room and verify that there aren't other people there. It will be recording your screen. It'll be recording your browser activity, anything you do in your web browser. It'll be recording the webcam, the screen, the browser activity, and the audio. It's really not that bad. I will set up a practice quiz in HonorLock. The hardest part for most people, at least, so when I had to try to get a group of college algebra students through the HonorLock process, by far the hardest thing was getting them to go through the identification verification process correctly. But that's more an issue with college algebra students not wanting to follow directions or read anything. That's a good question. I'm not sure how HonorLock will handle music. Nobody's ever asked me that before. I don't know. I wouldn't be terribly surprised if it flagged you for it, but it shouldn't pull you out for it. So if you get flagged, that's not the end of the world. That just means that they're going to tell me to review the video and stuff. Definitely no headphones. Yeah, I know headphones are not going to be okay for the obvious reason that somebody could be piping information to you through them. But as long as the music is coming through speakers and it's not so loud that it drowns out everything else, like not so loud that you could be having a conversation which couldn't be heard, then I think it would be okay. I would say music will probably be okay. Just keep the volume down. If they give you shit, just roll with it. You know, if we have to turn off the music, it's not the end of the world. But that might be a good question. Send me a Canvas message about that, and I'll send something to HonorLock, or you can ask HonorLock support directly. It would be good to get that cleared up before the test so it doesn't cause trouble. Yeah, if your only mechanism for listening to music is headphones, I don't think that will be allowed during the test. Just like during class, right? There's no way that I would allow someone to wear headphones during a testing class. For the same reasons, we can't be doing that here. I apologize if that's unpleasant, but you know, it is an exam, right? So we gotta show it the same respect we would show an in-class exam. These are good questions. Some of these things are things I've never thought about. Is there any other questions that you guys would have for me, or that you would like me to pass on to HonorLock, or anything like that? Okay. If not, then I vote that we look at an example or two of trig integrals. And I would be happy to work any that you guys would like. So are there any problems from the homework that you guys, that you guys would like to take a look at? All right, and while we're deciding which ones to do, I will go ahead here and reschedule this to this Friday. See if I got a little bit more time to grind on it. Come on, WebAssign. You can do it. 15 seems to be a popular one. Yeah, we'll make sure to do 15. We've got a few votes for 15, 19, and 6. Let me get this scheduled and then we'll take a look. So Friday's class. Make sure this key is off. All right, let's do 15 first. 15 is definitely, oh, that's not bad. You guys can do this. 15, 6, 19. Okay, we'll go in order. Let's do 6 first. So that's the 6th power of tangent times the 7th power of cosine, or something like that. I'll write it down here and then switch back to the dot cam. So at a glance, this problem doesn't appear to be one of the problems we learned how to solve. It's not a power of sine times a power of cosine, or a power of secant times a power of tangent, at least at a glance. But I can write it as a power of sine times a power of cosine by rewriting tangent as sine over cosine. So the 6th power of tangent, that's sine x over cos x all to the 6th times cos to the 7th x dx. So this is how I would get started on number 6, which is the integral of the 6th power of sine x over the 6th power of cos x times the 7th power of cos x. And you can cancel 6 of these into that, and you get the 6th power of sine times the 1st power of cosine. Everybody with me so far? So this is a 6. So I've got 6 copies of cosine downstairs, 7 copies of cosine upstairs. So what survives is 6 copies of sine and 1 copy of cosine. Now this is one of our sine cosine integrals. Here the power of cosine is odd and the power of sine is even. So I'll grab 1 copy of the odd guy to set aside with the differential. Oh, that's already done. Here, I've just got 1 copy of that guy to hang out there. There's nothing else. So from here we substitute. We substitute for the other guy. So we're going to let z be sine x. dz then is cos x dx. And I don't need to worry about any limits because it's an indefinite integral. So the whole game here is really just writing tangent as sine over cosine. All right, once we do that, this turns into a fairly straightforward substitution problem. Under this substitution, this integral just becomes z to the 6 dz. All right, because cos x dx, that's dz. And sine is z. So this is z to the 7 over 7 plus a constant. So that's the 7th power of the sine function over 7 plus a constant. Not too bad. Good warm-up problem, though. So remember, the reason I taught you to do trig integrals the way I did, powers of sine times powers of cosine, or powers of secant times powers of tangent, is because any combination of trig functions can always be rewritten as one of those or a sum of things like that. So if the thing you're handed doesn't look like that right away, your first task should be to do some algebra and make it like that. Unless you see some other obvious path. But that's, if you're looking for an algorithm you can always follow, that is an algorithm which will always work. Questions on this one? Okay, then let's, get this out of the way. Knock it over wherever I put it, aren't I? So a couple others that were very common requests. I think I saw like 15, 16, and 19 in there a few times. Let me see what was really, what were we looking for the most? Oh, okay. 5. I see 15 was requested a few times. 5, 5, 5, 5, 19. All right, let's do 5. I hear you. Sine squared times cos to the 4. All right. I'm not going to have the 9 in mind. All right, the red constant there is random. It'll be different on yours than it is on mine. So I'll do the integral from 0 to pi of sine squared x cos to the 4 x dx. Yeah, this problem kind of sucks. There's really no getting around it. Because both of the powers are even, right? The sine cosine integrals are tricky when both of the powers are even. We will not be able to make a substitution to turn this into a polynomial, unfortunately, right? So the nice case for the sine cosine integrals is at least one of the powers is odd. This is the not nice case. In the not nice case, the only thing we can do is beat these things to death with the following identities. Which I will write here in terms of theta so that we can substitute in them later to get the other versions that we'll need. So we're going to use these. because both powers are even. There's nothing else we can do really. So my integral is the same as the integral from 0 to pi. Sine squared of x is 1/2 1 minus cos of 2x. That's sine squared. Cos to the fourth is cos squared squared. So in this step, I'll just write it like that. I can pop out my 1/2. There will be 2 more. I have the 1 minus cos 2x. And then this cos squared, he's 1/2 times 1 plus cos 2x all squared dx, like that. This square is this square. And the cosine squared inside, I replace by 1/2 1 plus cos 2x. I need to give the square to the 1/2 and to the binomial involving cos 2x there separately. 1/2 squared is 1/4. I've got a 1/2 out front already, so that will be 1/8. Integral 0 to pi 1 minus cos 2x times 1 plus cos 2x squared dx, like that. So just handling the constant term. Now from here, I need to FOIL this out, then distribute this over that, and then march on. The nice thing is that everything is now in terms of cosine 2x. So down the road, I'll be able to use this identity again. But for now, this is 1/8 times the integral from 0 to pi, 1 minus cos 2x, times, if I FOIL this out, that's 1 plus 2 cos 2x plus cos squared of 2x dx, like this. And now I need to distribute the 1 minus cos 2x term over this trinomial in cos 2x. So what will I get when I do that? Just do it carefully. 1 times 1 is 1. 1 times 2 cos 2x is 2 cos 2x. 1 times cos squared 2x is cos squared 2x. And now from that, I'm going to subtract, distribute the cos 2x terms. So minus cos 2x times 1 is minus cos 2x. Minus cos 2x times 2 cos 2x is minus 2 cos squared 2x. And minus cos 2x times cos squared 2x is minus cos cubed 2x. So this is where I land. And in my next line, I am going to combine like terms. Take a second, make sure you agree with me up to here, make sure everything's looking good. Ew is, yeah, the appropriate reaction to this. This is an unpleasant thing. But you know, we do what we must. So we bravely saunter on. If I combine my like terms, I get 1/8 integral 0 to pi. There's only one constant term, and it's 1. What about my regular cosines of 2x? Well, here's plus 2 of them, minus 1 of them. So I just have one copy of cos 2x, right? These guys are like terms. So I'll have plus cos 2x. Then also these guys are like terms. Here I have one positive and two negative, so I'll have minus cos squared 2x. He's going to require a little more double angle, half angle stuff. And then I've got my minus cos cubed 2x. Before I proceed to an antiderivative step, I need to do something with this cos squared. I'm going to have to do something different with the cos cubed. But first, we know what to do with this guy. He's again an even power, right? It's sine to the 0 times cos 2. So he's going to be another one of these identities. Where are you? Another one of these identities up here. So if I plug theta equals 2x, then I get cos squared of 2x equals 1/2 times 1 plus cos of 2 times 2x is cos 4x, like that. This is a 1/2 here. So that's what I'll do with the cos squared 2x term. The cos cubed 2x term is actually easier to handle than that. But first, let's just come down here and write what we've got. And then again, I'll combine like terms. So that gets me to here. I'm going to distribute that 1/2 and combine the 1/2 with the 1. So this 1 and the minus 1/2 that will come from this will give me a positive 1/2. Then I'll have this cos 2x term here. Then I'll have minus 1/2 cos 4x. And then my minus cos cubed 2x, still lingering there. So now these three pieces are ready for the antiderivative step, but this piece requires a little bit of thought on his own. Anybody got any ideas what we can do with the cos cubed of 2x? Or what if I just asked you to integrate cos cubed theta? I see it there. All right. So cos cubed, yeah, is an odd power, right? That's like sine to the 0 times cosine to the 3. So the sine power is even and the cosine power is odd. So we're going to try a u sub thing. Fernando has it. We're going to write cos cubed as cos squared times cosine. The 1/2 came from combining this term with the 1/2 I get when I distribute here. So this would be 1 minus 1/2, which is 1/2. That's where the constant term there came from. So I distributed the 1/2 to the 1 plus cos 4x. Here's the 1/2 times cos 4x. 1/2 times 1 is 1/2. So when I subtract 1 minus 1/2, I get 1/2 here. All right, this piece is really minus 1/2 cos 4x. And then the cos cubed, there was one correct answer there. I'm going to treat him as cos squared times cos, and then the cos squared I will rewrite as 1 minus sine squared, and we will attack it from there. At this step, I want to go ahead and complete the antiderivatives for the first 3 pieces. 1/2 will integrate to 1/2 x, plus cos 2x will integrate to 1/2 sine 2x. Cos 4x will integrate to 1/4 sine 4x, so this will be minus 1/8 sine 4x, all evaluated from 0 to pi. Then minus 1/8 integral 0 to pi cos cubed of 2x dx. So this one requires a different approach than these, so we'll go ahead and knock those out. Good news is that there's very little contribution from any of this shit. Most of this shit is 0. First, any questions about the antiderivatives here and here, those little micro u subs that we're getting very fast at now? So kind of running in the background here, I'm using the fact that the integral of cos ax is 1 over a times the sine of ax plus c. Good thing to be able to do very, very quickly. Things like this, like integrals of sine ax, are very, very similar. They just have a negative. And we should be to a place now where we can do those quickly. Of course, the integral of 1/2 is 1/2 x. All right, so let's evaluate this. And at the same time, let's also rewrite this as cos squared times cos. I have my 1/8 out front. When I plug in pi, the sine of 4 pi is 0. The sine of 2 pi is 0. So the only contribution comes from this guy. When I plug in 0, the sine of 0 is 0, the sine of 0 is 0, 1/2 times 0 is 0. So the only contribution from this whole thing comes from this term when I plug in pi. That's it. That's the whole bracketed piece. The other 2 pieces give 0 at both the upper and lower bounds. So I have that minus 1/8 integral 0 to pi cos squared 2x times cos 2x. The cos squared of 2x I will rewrite. So remember that sine squared theta plus cos squared theta equals 1, which means cos squared theta is 1 minus sine squared theta. Plug theta equals 2x. And you see that cos squared of 2x is equal to 1 minus sine squared of 2x. So we will be making use of that here, and then splitting and doing a substitution. Any questions on the antiderivative step here to here, or the evaluation step here to here? I'd like to get those out of the way now if there are any. That'll just help with the flow. Feel okay? It's all right if you have questions. This is the perfect time for questions if you have them. So please, if you have them, ask them. Okay. So this is pi over 16 minus 1/8 integral 0 to pi 1 minus sine squared 2x times cos 2x and then I can distribute the cos 2x term. And notice how this is all one unbroken line, every line equal to the previous. We're not leaving anything out, we're not skipping, or all of our side work is off to the side. As you do these problems, please try to organize your work this way. Let the page do the organization for you. You try to keep this shit straight in your head, it'll all fall apart, it'll never happen. But if you let the page remember for you, it will be okay. I now distribute the cos 2x. I get cos 2x minus cos 2x sine squared 2x dx, like that. Next, I'm going to split up this integral. This one will be done via a substitution. This one is a straightforward micro u sub thing. So this is pi over 16 minus 1/8. The antiderivative of cos 2x is sine 2x over 2, so it's 1/2 sine 2x, and that piece needs to be evaluated from 0 to pi. And then I have minus 1/8 integral 0 to pi cos 2x sine squared 2x dx. And here I will substitute for sine of 2x. The evaluation step here is trivial. Sine of 2 pi is 0, sine of 0 is 0. This piece contributes nothing. This whole thing is 0. And I guess if we were really thinking ahead, if I was able to see far enough ahead, then rather than splitting these, I would have played this game and combined that cos 2x term with the cos 2x term here. But this is fine, so no contribution from him. In this integral, I want to make the substitution. I'm going to run out of space, aren't I? Z equals sine 2x dz then is cos 2x. That's a chain rule derivative. My lower bound, oh really? No, I don't believe it. Nothing from this either, huh? Yeah, this is fascinating. I should believe it, I know this, but so my bounds are funny here, right? When x is equal to 0, z is the sine of 2 times 0 is also 0. And when x is equal to pi, z is equal to the sine of 2 pi, which is also 0. Fascinating. I wasn't expecting that. This is to do with the particular limits we chose. You remember last week we talked a little bit about Fourier series, Fourier analysis. Sine and cosine are what are called orthogonal functions. Orthogonal in the sense that they meet at 90 degrees if you impose a certain geometry on the space of all functions. This is something operator theorists do quite a bit, which means that a lot of the integrals of sine times cosine are going to come out to 0, and this is another one of those. So here, look at this. When my lower bound, x equals 0, is plugged into this substitution, z is the sine of 2 times 0, which is the sine of 0, which is 0. My upper bound, when x is equal to pi, I plug that in here, and I get z equals sine of 2 pi, which is also 0. So this becomes, this is so silly. My differential term was 2 cos 2x, so I'll have another copy of 1/2 coming out, but it's irrelevant. Because it's multiplying the integral from 0 to 0 of sine 2x z, so that's z squared. And then cos 2x dx, that's 1/2 dz, that's where the 16 is coming from here. But of course, the integral from 0 to 0 of z squared is 0. So this whole apparatus is just pi over 16. You can write this as minus 1/16 times 0, because you're integrating from 0 to 0. So the whole thing here is pi over 16. In other words, the only contribution in this whole motherfucker came from this guy. None of this shit gives us anything. Cute, right? Maybe even a little infuriating. All right. I like those reactions. Yeah, I don't blame you. It does smell like goofiness. So if you want, oh, don't be mad. If you want, I'm going to show you something here you're not supposed to know. You ready? First, before we do this, questions. It's important that you understand this process. I could give you this as an indefinite integral, right? Forget the bounds, and then all this shit matters, okay? Let's be clear about that. This is not a meaningless problem because those things came out to 0. The only reason they came out to 0 is because we're using the particular bounds 0 and pi. Otherwise, this would be a tough problem with a big answer. Yeah, sort of. So the observation that since this is so simple, there ought to have been a shortcut is almost true. It comes back to Fourier analysis again. The integral in the last piece here is z cubed over 3 evaluated between these two bounds, but those two bounds are both 0. So the integral, so there's a rule here that you may or may not remember. The integral from a to a of f of x dx is 0 for any integrable x. Let's say for any continuous function f of x. So that's how I conclude that that last piece is 0. You could write it as z cubed over 3 and then evaluate between those two bounds. You'll still get 0. All right, what else are we wondering? Let's worry about the technical stuff first, and then I'll show you the cool weirdness. Yeah, we'll get there, Simon. So it did take up quite a bit of space. If I don't think it's quite 3 pages. It's most of 2 pages, you know. So here's the whole thing. It starts here and it ends down here. So it's 1 page front and back. It's like 1.5 pages. Not unheard of for a problem in Calc 2 to take several pages, though. This is not an especially long problem. It's about par for the course. But there is something cool here that is related to this that I would like to show you. It's unfortunate that you guys haven't had any linear algebra yet. If you had a good pre-calculus class, then you talked about linear algebra a tiny, tiny bit. There's something called the dot product between two vectors. There's two ways to interpret the dot product. It's the magnitude of the two vectors multiplied times the cosine of the angle in between them. So if u and v are two vectors, then I can find the angle between them. And the dot product between the two things allows you to define the angle between them by this relation. Sorry, I wrote the v first. It turns out that this allows us to talk about the angle between all sorts of things that you would not think you can talk about angles between. Functions are vectors. Functions are vector space. Functions are also vectors. In the vector space of continuous functions. So I know some of you took 1140 with me. A vector space isn't just a place with arrows. A vector space is any set in which you can find a way to define addition and multiplication by a constant. I can add two continuous functions, I get another continuous function. If I multiply a continuous function by a constant, I get another continuous function. So the space of all continuous functions is a vector space. There is a notion of a dot product in the vector space of continuous functions, and it's the integral. So if I think of two functions, f of x and g of x, as vectors, I can define their dot product as the integral of f of x times the integral of the complex conjugate of g of x. And here you would integrate over wherever, say on 0 to pi, because that's what we're doing. Since I have, don't write any of this down, please. You're going to clutter your notes with this shit. We're just talking. If you have a concept of a dot product, then you have a concept of an angle between two functions. Since I have a notion of a dot product in the land of continuous functions, where I think of the functions themselves as the vectors, I have a notion of being at 90 degrees. Recall, two vectors u and v are said to be perpendicular. That's what this upside down capital T means, if and only if their dot product is equal to 0. The dot product in the land of continuous functions is the integral. And if g of x is a real valued function, then his complex conjugate is the same as g of x itself. Which means two functions, f of x and g of x, are perpendicular, or another word for that is orthogonal, in the vector space of continuous functions on 0 pi, which is denoted by c 0 pi, means that their dot product is equal to 0. But that dot product is the integral from 0 to pi of f of x times g bar. But since g is real, that's just the integral of f times g. Now you might be able to smell where this is going. Sine and cosine are perpendicular to one another. They're 90 degrees out of phase. If there's any notion of orthogonality in function land, it should be the case that sine and cosine are perpendicular, which means the integral of sine times cos should come out to 0. And more generally, there's a big theorem. It's one of the major theorems in early Fourier analysis. Sine mx is perpendicular to cos nx, unless m and n are identical. So integrals of products of sines and cosines often come out to 0. They almost always come out to 0. Now we had powers of sine times powers of cosine, but you can use certain trig identities to reduce those to things like sine of some constant times x and cos of some constant times x. So there is something heavy going on here in the background, and it is good shit. I'm sorry for the diversion. I will paste a link for people who want more. The Wikipedia page discusses the origin of these things. Yeah. The orthogonality relation. All right, this is the good stuff right here. Yeah. Find it. Let's see, this might be good. This is good. Okay. All right. Orthogonal functions. This is relevant and tasty. So I'll paste it into the chat. If you want more on that, see there. That page is going to be very general. We're going to be talking about different vector spaces of functions, but the very first example, for good reason, is these guys. And then orthogonal polynomials. This is actually a huge area of research. There are people at UF who do this research. One of my favorite mathematicians is actually at UCF right now, and he's been doing very important work on orthogonal polynomials. The fuck is his name? Huge guy. I can't remember his name. But anyway, it's good stuff. Here's the other one. Read about it if you want to. Basically, you can impose geometry on weird spaces. The set of all continuous functions over any particular domain turns out to be a space where you can impose some geometry. And there's a lot to be learned if you're willing to take the time. It's quite beautiful. But we need to move on. So the other one that you guys really wanted to see was number 19. Let's take a quick look at that. It's a volume problem. So y is 5 sine squared x, and then we've got y equals 0, and x is between 0 and pi. I want to rotate about x-axis. Okay. So, yeah, good stuff, good stuff. So I'll start with a sketch of this curve. You could be forgiven if you don't know what sine squared looks like. If you take the regular sine wave and you kind of force all the negative parts to be positive, it looks about like that. I'm going to mark this as pi. Sine squared from 0 to pi kind of looks parabolic. So if that's 5 sine squared, then this max up here is 5. He would continue on something like this, but I don't really care because I'm only interested in what happens between 0 and pi. So y equals 0, that's the x-axis down here. That's also my axis of rotation. So this is my region. Given what the region looks like, which method should we use? Cylindrical shells or disk washers? Yeah, definitely a disk thing, right? If I wanted to use cylindrical shells, I would have to draw my strip in left and right. But then because this function isn't one-to-one, I couldn't talk about the length of that strip neatly in terms of this function. So I draw my strip in here perpendicular to the axis of rotation because I want to use the disk washer method. If you don't see why to use the disk washer method right away, go ahead and try to set it up with cylindrical shells. See why that's a challenge. Remember, disk washer method, your strip is always perpendicular to the axis of rotation. Cylindrical shells, your strip would always be parallel to the axis of rotation. Here, a strip that's parallel to the axis of rotation would be side to side, and the length of that strip, the thing that we call h in our formula there, you would not be able to find a nice expression for, just because of the algebra, because this function is not one-to-one. I do need to characterize this point. Remember, I always think of this thing as occurring at an arbitrary x value that I just call x. Its thickness is, of course, a dx thickness. And that means this point up here is x, comma, 5 sine squared x. Because I'm on the graph, y equals 5 sine squared x. Okay, any questions about what we've done so far? If you're uncertain about the graph, you're welcome to double check in Desmos. Sorry, this is from my Cop 1 class this morning. So you see it's like this. Here is my region from 0 to pi. I guess I should be, yeah, I'm doing a bad job drawing this. This should come in here kind of gently, not so sharp. This should come in here kind of gently, like that. Okay. If I rotate just that strip about this axis, that will generate a disk looking thing. Having a very, very small differential thickness, dx, and a radius, capital R. Little r here is 0 because my strip extends all the way to the axis of rotation. Because there's no gap between the strip and the axis of rotation. So I just have to worry about big R. And in this picture, big R is this distance, which is 5 sine squared x. So dV, the volume of that little differential solid, is pi times big R squared minus little r squared dx, which is pi times big R is 5 sine squared x, so this is 25 sine to the 4x minus 0 dx, which means v is the integral of dv taken here from 0 to pi, because that is the smallest x value in my region to the largest x value in my region of dv, which is pi times the integral from 0 to pi of 25 sine to the 4x dx, which is not a super nice integral, if I'm honest, for the same reasons that the last guy was not super nice. It's an even power of sine or cosine. I'll pop out the 25, and I get 25 pi integral 0 to pi sine squared x all squared, to which I apply my half angle formula. So that volume is 25 pi times the integral from 0 to pi of 1/2 1 minus cos 2x all squared dx, which is going to give me 25 pi over 4. I may stop a little bit short on this one, guys, because I do want us to get to the new material. I'll FOIL this out. We'll have 1 minus 2 cos 2x, 2 cos 2x, plus cos squared 2x dx. Sorry, I'm running out of space there. So this is 25 pi over 4 integral 0 to pi 1 minus 2 cos 2x plus cos squared 2x. Now I rewrite as 1/2 1 plus cos 4x and then I can distribute the 1/2 and combine my like terms, and I get 25 pi over 4 integral 0 to pi. 1 plus 1/2 is 3/2 minus 2 cos 2x plus 1/2 cos 4x dx. And just like in the problem we did a second ago, the only contribution is going to come from the constant term, because here I'll have a sine 2x evaluated from 0 to pi will give me 0. Here I'll integrate to a sine 4x in between these limits. That's also 0. So I will jump to the result and let you fill in any missing bits. This is 25 pi over 4 times 3 pi over 2. The other terms contribute nothing. So if you want to, you can clean this up and write it as 75 pi squared over 8. But that's the game. Okay, we do have to talk about new stuff. So again, if you want to go through this more carefully, I invite you to do so. Please just rewatch the video or come by my office hour. But now we do need to introduce the new stuff. if you weren't able to get all that in, just leave some space in your notes. And get ready for something cool. Because trig sub is really cool. One of the things that drives pre-calculus, Calc 1, and Calc 2 students crazy is that square roots really don't play nice with addition or subtraction. Issue. It's hard to simplify. Or work with stuff like the square root of 1 minus x squared, or the square root of 9 plus x squared, or the square root of x squared minus 4. These are not equal to 1 minus x, 3 plus x, or x minus 2, respectively. Right? Square roots don't ever distribute over addition or subtraction. And for that reason, each of these functions is kind of tough to integrate. They're not power rule functions. I can't just apply a power rule because I can't give the square root to the pieces separately. And unless I have an x floating around in the integral to substitute, like for the 1 minus x squared, I could try substituting for that, but I would need a copy of x in my integral to absorb the differential term. So integrating each of these on their own is hard because algebraically they're not very nice. However, if we let x be sine theta, then 1 minus x squared is 1 minus sine squared theta is cos squared theta by Pythagoras. Right? Sine squared plus cos squared is 1. So 1 minus sine squared is cos squared. Thus, the square root of 1 minus x squared would become the square root of 1 minus sine squared theta, would become the square root of cos squared theta, which is just cos theta as long as cos theta is positive. If cos theta isn't positive, then you'd get the absolute value of cosine theta here. But we're going to assume that cos theta is positive. And throughout section 7.3, every time we encounter something like the square root of cos squared theta, we're going to assume that it really does just simplify to cos theta. It's a mild simplifying assumption. If you want to worry about the details of the absolute value thing, we can. But it's not something that you need to stress about here. I need you to learn the technique. So the first and most important thing to remember for section 7.3, this shit never simplifies to this. This never simplifies to this. This never simplifies to this. None of that shit works. But we can get around it by replacing the variable with an appropriate trig function so that the Pythagorean identity for that trig function leads to the square root simplifying. Similarly, if x is 3 times the tangent of theta, then 9 plus x squared would be 9 plus 3 tan theta all squared is 9 plus 9 tan squared theta. You can factor the 9, and you get 1 plus tan squared theta, which is 9 secant squared theta. So the square root of 9 plus x squared would be the square root of 9 secant squared theta, which is 3 secant theta. And if x were 2 secant theta, then x squared minus 4 would be 4 secant squared theta minus 4, which is 4 times secant squared theta minus 1, which is 4 times the tan squared of theta. So the square root of x squared minus 4 under that substitution would be the square root of 4 tan squared theta would be 2 tan theta. In other words, if you need to do stuff like an integral involving something that looks like this, something that looks like this, or something that looks like this, you can make a trigonometric substitution. You can substitute x equals some appropriate choice of trig function such that the square root will clean up nicely by using the Pythagorean identities. This is the brilliance of trig sub. Yeah, pretty much hacking the mainframe. So let me show you a little bit how this looks in practice. Hey, baby.
Gotcha.
Oh, thank you. You're the best. I'll give you a rule for which substitutions to use when. The thing you need to be careful about here is changing your bounds and how to go back to the original variable in an indefinite integral. So first, as an example problem, let's find the area of the circle radius r centered at the origin. Remember, the equation of such a circle is x squared plus y squared equals r squared. If I solve that for y, I get y equals the square root of r squared minus x squared. The positive square root just gives me the upper semicircle. This is r comma 0. Up here is 0 comma r. The lower semicircle would come from the negative square root. So if I find this area and I double it, then that will give me the area of the whole circle. Over here is negative r comma 0. So the shaded area is equal to the integral from negative r to r of this guy, r squared minus x squared dx. Now he, I can use a symmetry argument on, still just playing around. That's twice the integral from 0 to r of r squared minus x squared dx. Therefore, the area of the circle is equal to 4 times the integral from 0 to r of the square root of r squared minus x squared dx. So this is my goal. I want to do this integral. So are we all comfortable with this idea that the area of the circle is 4 times this integral? That's the setup here. I just need to get us to a place where we need to do the integral. Think of this integral as measuring this area here. The integral measures that area in quadrant 1, and since the circle has this symmetry, I just multiply by 4. Yeah, so Caesar, good question, right? Why the 4? The integral there is the integral of this function, the square root of r squared minus x squared taken from 0 to r. And that's exactly 1/4 of the circle. The circle has this symmetry. So it's like I've sliced the circle into 4. It was easy to find a representation of that area as an integral. So I multiply that by 4 and I get the whole thing. So my task is to evaluate this integral. And the neat trick is the trigonometric sub. It's a little bit backwards. Usually when I make a substitution, I let my new variable be some combination of the old variables. Like I might try to substitute, z equals r squared minus x squared or something. Here, I'm going to go the other way. I'm going to let x, my old variable, be some trig function of the new variable theta. So I'm going to make the trigonometric substitution x equals r sine theta. I'll tell you how to pick this number and how to pick this function after this example, so please hang in there with me. I need to calculate my differential and I need to change my bounds because I'm still making a substitution. Trig sub is still just a substitution. It's just a clever one. Dx, if I take the derivative, I get r cos theta. So dx is r cos theta d theta. Another nice thing about trig sub, since I'm using my old variable equals a function of my new variable, I don't have to force the differential in. I'm just going to plug it in. I'm just going to plug in r cos theta d theta for dx. So trig sub is, in a sense, easier. When x is equal to 0, theta, I'll have r equals r sine theta. Divide both sides by r, I get 1 equals sine theta. And so theta is the inverse sine of 1. The inverse sine of 1 is pi over 2. So theta is pi over 2. I'm sorry, I said when x is equal to 0. This should be when x is equal to r. Sorry. So to find my new bound, I take the old bound, x equals r, and I plug it into my substitution. When x is equal to r, I get the equation r equals r sine theta. R equals r sine theta. I need to solve this for theta to find my new upper bound. If I divide both sides by r, I get 1 equals sine theta. And then I take the inverse sine of both sides, and I get theta equals pi over 2. When x is equal to 0, I get 0 equals r sine theta. Divide both sides by r, you get 0 equals sine theta, which means the inverse sine of 0 is theta, which means theta is 0 because the inverse sine of 0 is 0. Normally, I would not write a lot of these in between steps, but here I'm just trying to help you see where this comes from since it's the first time we're doing it. I've got my old upper bound on the bottom. That was my goof, I'm sorry. I just wrote the thing in the wrong place. 0. So Simon asks, is the inverse sine of 0 0 or 2 pi? You could also ask, could it be pi? You need to go back and remember the definitions of the inverse trig functions. Very important, right? Very important. If you look at the trig necessities for this class, the definition of the inverse trig function is a big idea. The inverse sine function only ever spits things out that are between negative pi over 2 and pi over 2. So remember, A equals sine inverse of B means the sine of A is equal to B, and this is important, negative pi over 2 is less than or equal to A is less than or equal to pi over 2. So to get through this section, you must know the definition of the inverse trig functions. You have to be comfy with these restrictions. All right, so let's finish this up. What does my integral become? So the area of circle is 4 times. My old lower bound of 0 stays 0. My old upper bound of r becomes pi over 2. The square root of r squared minus x squared is going to be the square root of r squared minus r sine theta squared, because I'm plugging in r sine theta for x. And then dx is r cos theta d theta. The magic of this substitution is that this square root will clean up nicely. All right, I know we're a little bit over time, but I'm going to ask you to hang in there just through this example if you can. I have the square root of r squared minus r squared sine squared theta, and then r cos theta d theta hanging out. I'm going to simplify under the square root. I have 0 to pi over 2. Factor in r squared, and what's left is 1 minus sine squared under the square root. And then r cos theta d theta still chilling. Finally, that's 4 integral 0 to pi over 2 square root of r squared cos squared theta times r cos theta d theta. 1 minus sine squared, this is cos squared by Pythagoras. So now I can take the square root because there's no more addition or subtraction under there. The square root of r squared cos squared theta is r cos theta. So you get r cos theta times r cos theta d theta. R squared comes out. Integral of cos squared theta d theta remains. That integral is done via one of these half-angle identities because it's a sine-cosine integral where the powers are even. The antiderivative step here is not hard. I'll pull out the 1/2 as an over 2. 1 d theta integrates to theta, cos 2 theta integrates to sine 2 theta over 2, and we evaluate from 0 to pi over 2. No, he has not been fed. At the lower bound, both of these are 0. At the upper bound, this guy is pi over 2. This is the sine of 2 times pi over 2 is the sine of pi. 4r squared over 2 is 2r squared. And then in here in my evaluation step, I have pi over 2 plus 0 minus 0 plus 0. So at the end of the day, I get 2r squared times pi over 2, or just pi r squared, which we all knew is the area of a circle of radius r. But before this, we haven't been able to calculate that as an integral. So the last thing I want to do, so that you guys can, if you want to, between now and Wednesday, work on the new homework, which will be coming out in just a few minutes. I'm going to give you the trig sub Bible. Right? It's a little table of what you see in your integral and what to substitute. So think of this as like the Lipet rule, but for trig sub. It tells you what to do. Thank you guys for hanging around. We had a few little deviations in our conversation today. If your integral contains, substitute this. So if your integral contains a square root of some constant squared minus some variable stuff squared, this is an a squared. So if you've got like a square root of a squared minus u squared, you're going to substitute u equals a sine theta. If your integrand contains a square root of a squared plus u squared, you're going to substitute u equals a tan theta. And if your integral contains a square root of u squared minus a squared, you're going to want to substitute u equals a secant theta. It's important that you don't forget the differentials. If u is a sine theta, then du is a cos theta d theta. If u is a tan theta, then du is a secant squared theta d theta. And if u is a secant theta, then du is a secant theta tan theta d theta. And this comes from the Pythagorean identities, right? It's because of the Pythagorean identity sine squared plus cos squared equals 1 that this will clean up nicely if you sub that in. Okay, so this is what you need to get started in your trig sub adventures. Yeah, I've already extended the homework that was due today to Friday. That's due on Friday. But I am going to open up your 7.3 homework. It may also contain a little bit of 7.4 because this week we're going to cover 7.3 and 7.4. So try to finish up homework 4, get that done today, and then dive in and work the first few 7.3 problems. Wednesday, I'm going to go back over this table. I'll give you a slightly more detailed version of this, and we'll work a lot more trig sub examples. And then we'll also start our discussion on partial fractions, which is section 7.4. And then on Friday, we will continue talking about partial fractions, and I will also give you your study guide for exam 1. Any questions, guys? Okay, so I'm going to go ahead and end the meeting here for today. Again, thank you for sticking around. I know we went a little bit over. I'll get the video posted as soon as I can. Your homework from last week has been extended. Your new homework will be coming out in just a few minutes. And I will see you all either in the office hour, which is what I'm switching over to now, or in class on Wednesday. I hope you guys have a lovely afternoon.